mentioned previously, like in the surface hydrology course, you will learn things about like precipitation and measuring precipitation, evapotranspiration type and how to estimate evapotranspiration, measuring stream flow and hydrograph analysis and open channel flow. So you'll learn this in hydrology and hydraulics course. Soil moisture infiltration and percolation, you'll learn this also in the hydrology course or a soil science course. But the main part of this course is properties. That's need to understand like aquifer property in order to understand groundwater flow, and you need well hydraulics. We will also touch about like in this course about things like groundwater surface water interaction, mainly when we talk about like groundwater flow, uh, uh, groundwater interaction with coastal system and contaminant transport. These are each of these like is a course on its own, but I will try to touch like a little bit on it also in this course. Okay, you like the properties of the aquifer. If you want to read and learn more beyond this video and slides, you can check like either this book or that book, whichever you prefer. This book is available for free. This is your recommended textbook. You need to buy it. Uh, okay, if you want to read it, but you don't have to read both of them. You can read either if you need to read more. Yeah, you can read either of these like in these chapters. Okay, so let's get started with the first lesson in the properties of aquifer, which is porosity and the specific yield. So in this video you will learn, by the end of this lesson you should be able to define porosity and define something like what is porosity versus effective porosity. You should be able to also know the difference between primary and secondary porosity, and you should be able to have like a feeling of porosity of different rock, like subsurface material, like sedimentary material, metamorphic or volcanic rock. You should be able to see the different porosity of this different material, and finally explain specific yield of an sediment or like rock or of an aquifer, and it's important like see the importance of this specific yield. Okay, so let's just get started. Yeah, uh, one thing like so the reason I'm giving to you at the beginning of the lesson, because the participation activity for this lesson is basically like you ask one question about this lesson and you answer two questions. Like so you will ask one question, your classmate will each will ask at least one question, and then you answer like two question, and and this note like answer unanswered question first. Like if all question are have responses, you choose those with fewer than two responses. Yeah, and basically like providing like a correct answer. Yeah. And like you'll get grade for answering a question, but you will also get just asking the question. You get grade for this. So remember, like you get grade for doing the exit ticket. You provide like feedback about the video. You get some grade for asking a question, and then you will get some grade also for answering questions. Yeah. Okay. So the reason I give you this as a beginning, like as you are watching this video, if you have any question, write it down, and that would be part of your participation activity. Okay, so let's get started. What is the porosity? Or even before we talk what is porosity, what's aquifer? Remember we defined aquifer before as something in the subsurface below the water table. So remember below the water table, as the definition of the water table, that's where you have zero gauge pressure. And what is below the water table? The sediments or rocks that is saturated with water where water can flow, that would be an aquifer. Here, let's define it from a geological, not hydraulic perspective, but a geological perspective. It is the ability to conduct or transmit water plus ability to hold water. So it's an underground storage that can transmit water. And where is this water? So this water, like you have sediments or you have rocks, and these sediments or rocks, they have cracks or voids, like which we call porosity. These cracks or voids, they happen due like to physical or chemical processes, like weathering processes, and we call this porosity. So what is the definition of porosity? Basically, porosity, it is the volume of void over the total volume of the rock. So like you have, let's say this is your, oops, I think I need to do something. Okay, here we go. Let's say this is your rock. So like, see here, that's like your sediments, yeah. So these are like the sediments, yeah. So these are the sediments here. And that would be like your total volume, yeah. And that would be the volume of like these solid, and that would be the volume of these void, like the void space, yeah. So basically, if porosity, what is porosity? So porosity, we usually refer to it at n. That is volume of void, yeah, over the total volume. What would be the total volume? The total volume would be the volume of void plus the volume of solid. Yeah, that would be the total volume. So it is like N is equal to volume of void over the volume total. Yeah. But what is effective porosity? So effective porosity is the porosity where water available for water to flow. What does this mean? Let me show you. Okay, so you see here in this figure, see this is your sediment, but what is the porosity that is available for water to flow? Like for example, is this porosity available for water to flow? No. Here, is this available for water to flow? No. Here. How about this? Is this available for water to flow? No. But like see, here is the porosity that is available for water to flow. Yeah. Like here, for example, like here, like here. See, is this porosity here available for water to flow? No, it is saturated with water, but water will not flow from here. Same here. So this is called like immobile groundwater, and this is called like mobile groundwater. This is all this here. See this blue here, immobile groundwater. See, all this is immobile groundwater. So effective porosity is the porosity that is available for water to flow. That's a very important distinction between like, so porosity is N, effective porosity is Ne. So this is the volume of void plus volume of solid plus volume of void, like the volume, this is like your V. The only difference here is this is the volume of voids, like all the voids, while this one is the volume of void space which groundwater flows. Like this volume where like groundwater can flow. Yeah. So let's look at an example. Like silt, for example, its porosity, it has very fine particle. Its porosity is 40 to 50%. Yeah, but its effective porosity is less than 1% to 5%, very small, like groundwater cannot flow. And that's why usually silt does not make an aquifer. Silt will make an fine sand, coarse sand, and well sorted and fine gravel, for example, or sandy gravel. You see they have like less porosities than silt, so you will see they will have like less porosities than silt, but much higher effective porosities than sand, because like sand, fine sand, coarse sand, and well sorted sand and gravel, sandy gravel, these will make good aquifer. Because remember, aquifer is store water and transmit water. So fine sands, this will make a good aquifer because water can flow. You have a big effective porosity. Like let's look, for example, at there's like 20 to 30%, and we will learn later why the porosity is not much, but the effective porosity is like 15 to 20. So very high effective porosity, also like the total porosity. Versus here, silt, the porosity is 50 to 40 to 50%. Porosity is very high, but the effective porosity where it's available for groundwater to flow is very low, like less than 1.05. That's very important distinction. And you will get, I think I will ask these types of questions also in the exam. Yeah. Okay. So try to look at this and try to look at these concepts. Here, these are again like just you can read this. You can pause this slide and read this again. I told you like this is the volume. Another definition for porosity. like you can say like this is the volume of void. What is the volume of void? That is the total volume minus the volume of solids. That will give you the volume of void. So the volume of void, that's your total volume minus the volume of solid. Yeah. Uh, okay. Another definition of porosity, alternative definition, is you can define it in terms of bulk density and particle density. So if you remember from your geotechnical engineering course, this is also important for if you're doing like contaminant transport. Bulk density, that's an important concept. So bulk density, what's bulk density? That's oven dry mass of solid mass over volume of the whole. So like that's like your volume. Okay, so here you have like your solid particles, yeah, and then you can have some water, yeah, you can have some water. But bulk density is that like you remove this water. Like how do you remove this water? You oven dry your sample. So you get your sample, you oven dry it, so you'll only end up with the volume of solid and the air, yeah. And the oven dry mass of solid mass over the volume as a whole. So this is called bulk density. Particle density is the same, oven dry mass of solid over the volume of solid. So here, this is the total volume. This is only the volume of solid, not the volume of air. So basically what we can do, we've seen this before, we've seen this before, we've seen this before, we've seen this before, but I could express like the volume VD, I could express this as and the total volume, I could express it by the particle density. So another definition for porosity could be like bulk density over the particle density of the sample. The bulk density, like if you, for those who study contaminant transport, I think you must know this number or you memorize this number. So for most rock and solid particle, the bulk density is like 2.65 gram per centimeter cube. Yeah? And again, remember effective porosity available for water. Okay. So let's go next. So now we will see that we will look at these 5 different things and we will see why they have different porosity. So what is the controlling factor? Is it because like of the grain size? Is it because of the packing geometry? Is it because of sorting, grain shape, and dispersive effect of electromagnetic charge? So for example, uh, well sorted sand and gravel, yeah, uh, has higher porosity and also higher effective porosity than sand and gravel mixed. Yeah, why is that? So we will see like why the well sorted will have like a higher porosity and effective porosity also than this one. Glacier till, for example, has much lower porosity. So silt has like a higher porosity than like these two. Clay will even have higher porosity than anything, yeah. But again, this one have high, like this one will have high porosity, but will have low effective porosity. This one, for example, has like low porosity and also low effective porosity. This kind of low porosity but high effective porosity. I mean low porosity compared to this one, yeah. So we will see like what are the factors that will control like these things. These basically are like these factors like grain size, packing geometry, sorting, grain shape, this and this one. So let's look at these factors one by one, yeah. So let's look here at the grain size. Sediments are classified on the base of their size. Like example, like a boulder, the size of individual grain would be about like what 30.5 like millimeters. That would be basketball, for example, the size of a basketball. Copals, for example, that would be the size of a grapefruit. Coarse gravel, that would be the size of a like a pea, size of a pea. Coarse sand, it has like the size range is like about 2 to 5 like millimeter, yeah, like half centimeter. So it would be size of water softener salt, for example. Medium sand, it has like its size is half millimeter to 2 millimeter, very small, like the size of a table saw, for example. Fine sand, very, very small, like size of half a millimeter. That's like a powdered sugar, and fines, that would be like the talcum powder. Yeah. So you can see here in this images, you can see like that would be like a fine sand, that would be like very coarse sand, for example. Like see, this is very fine. This is so. Is it because like when the size is smaller, like when the particle size is smaller, will that necessarily increase porosity? Actually, no. But I will show you this later. But before I show you this, I just want you to show you like, see, this is, for example, how sedimentologists commonly use grain size classification. So that would like that a sedimentologist will classify grain size in this way. Yeah. A soil scientist might classify them different. An engineer, as I will show you later, we classify grain size using something called ASTM 2488, and this was basically we classify them based on sieve size. Okay, but each one, like a sedimentologist, would be different than a soil scientist, would be different than an engineer in classifying. So, but I just wanted to show you this where you can find like these details. But let's see. Let me ask you a question. Yeah. Or actually, I give you the answer. The sphere actually does not, the diameter of the sphere does not influence porosity. Believe it or not, like if you have, and I mean, and that's true, because let me show you. Like if I just make a box around this one, yeah, what is the ratio of the solid to the void? Would it be different if it is like a smaller one? Like let me show you here. Like so, this is a big diameter, and this is a small diameter. If I show like the ratio of this solid, yeah, to this volume, would it be different than this ratio? No. So porosity of this one and this one is equal. So here, and for like this diameter, like small diameter, is equal to the porosity of this. Yeah. Why than like sand and gravel? Like because silt and clay, these are very tiny. Yeah. Remember silt and clay, that would be fine. Like something very tiny. Yeah. Something like even smaller than this one. This is bigger. Like so, why this one has a higher porosity if the grain size uh, does not matter? So let me ask you another question. Like which has a highest porosity? Well sorted sand or well sorted gravel? The same. Will have the same. Even though the sand and gravel, they have the same particle size, like bigger, like even though like the gravel would be bigger than the sand, but if they are both well sorted, they will have like the same porosity actually. Porosity will decrease. So but well sorted sand or well sorted gravel, they will have the same porosity actually. Okay. But then why now? The question is still like why silt? If grain sizes is not a factor, why does silt or clay has a higher porosity? That's actually due to packing. That's why it has a higher porosity, because like look here. So here packing two configuration represent extreme porosity of arrangement. So here packing of a sphere with porosity, like so here regardless of the diameter size, if I have this type of packing, yeah, the porosity will be, and you can divide like the area of a sphere, the volume of a sphere divided by the volume of a cube, yeah, with the diameter equal to the cube, yeah, side of the cube, and then you will find that the porosity will be equal to, it will always give you this regardless of this diameter. But with this type of packing, like with this type of packing, the porosity would be this. So like with this packing, you get the lowest porosity. With this packing, you get the highest porosity, and porosity value will differ in between. And that's why well-sorted sand and gravel varies from 50%, like this number here, it should be like 46.65, but it's just approximated to 50%, to like this number here, like 25%. Now we understand why well-sorted sand or gravel will have this porosity. It depends on packing. Now let's look at another thing. What is mixed here? So mixed here is that like it is so this is like well so packing here mixing here means that this is well sorted. Will like depending on packing, you will have like this. Mixed means that it's not well sorted. Like you have something here, yeah. You have other sediments here, and when you have these other sediments here, that will reduce the porosity, yeah. So let's look at this one, yeah. So so here this is like for example, sand, the gravel, and textile. Like we will now know why like these two has like lower porosities than this guy. Because here this is well sorting if sediment contains a mixture of grain size like poorly sorted. So this is well sorted, yeah, and this is poorly sorted. Okay, so this is well sorted, this is poorly sorted. So of course here the velocity is lower because you have only one grain size. Here you have many grain sizes, big and small. So this different, like when it's poorly sorted, you will these different grain size will fill these voids, and that's why. So like see, it's the same packing. Like see, remember this cubic packing has a porosity of 50%. So this guy will have a porosity of 56% if it is well sorted. But if it is well poorly sorted, this porosity will drop to like could drop to like 20 to like 30. Like it will generally drop to 20 to 35%. Yeah. Okay. Depending on like the packing. So this packing, for example, like it could drop to this. Yeah. So let's now look at other cases. So we've seen three things. We've seen the diameter size. We saw like diameter size is not a factor. Packing is a factor, and sorting is another factor. So let's how would we know if this sediment is well sorted or poorly sorted? So let me just review with you what you did in geotechnical engineering. So if you did this in geotechnical engineering, so one of the experiment that you or lab uh, experiment you has to do with like sieve analysis. Basically like you get a sample and you pass it through a sequence of sieves. If you keep shaking them and passing them through a sequence of sieves, and then like the big diameter one will be at the first sieve, the second diameter one will be at the second sieve, and so on until like you reach the sieve 200 where you have like the fine material, silt and fine. So like you keep doing this until like you reach sieve 200. Remember like sieve 200 that would be like number 200, like sieve 200. That would be passing the 0.0075 material. That will not like pass anything smaller than this number millimeter. So that for the will contain like the clay and the silt. So that is, yeah, if you remember this from your geotechnical engineering class. Okay. Uh, so here silt fine. So how do you remember like you did this in the geotechnical engineering class? So basically, what you do, you pass the material through this sieve, and then for each sieve, you what you will do, you will see how many, what percent of the material, for example, pass through like this sieve. See like the largest sieve, like this one, like here, like this one, like the largest sieve, almost everything pass. Here, like about 95% pass. So through each sieve, you see like what is the percent. So here, like the sieve 200, that would be 0.00. That would be this one. Okay, so you see like almost like that was like the remaining percent of like that's the materials that pass like this sieve. So you basically plot this and you You plot like this number, you connect like this curve, and after you connect this curve, remember like you did this, you calculate the uniformity coefficient. So the uniformity coefficient, this is basically the D60 over D10. What's D60? Like 60% of the material. And then so you go to here, D60, 60% of the material, and you get like this grain size, and 10% of the material pass here, you get like this grain size, and then you divide the D60 by D10, and you will get the uniformity coefficient. If uniformity coefficient is less than 4, this means it's well sorted. If it's more than 6, this means this is poorly sorted. And just by looking at this figure, so now my question to you, what is the uniformity coefficient of sample A and sample B? So here you have sample A, and this is sample B. And are the sample well or poorly sorted? Without calculating anything, I can just tell you, like, see, 60% past like this grain size here. I mean, my handwriting. I mean, past like this grain size, and 10% past this grain size. This means that they are, without doing any calculation, I can tell you that which uniformity coefficient. I can tell you that like is this guy like the uniformity coefficient of B, of sample B, of like sample B, would be like much smaller than the uniformity coefficient of sample A. And I can tell you that this would be like well sorted, and this would be like poorly sorted. Why this would be well sorted and this is poorly sorted? Because you see here, like their grain side are very near to one another, but here, see 60% pass here and 50 and like 10% pass here. So let's calculate it. So here basically like the 60%, like you have to read this number. It's like, so this is 0.5 here, 0.4, you get something here. So this is sample A, and so this is 0.2. Like it should be like, you know, if we drop this point, it should be somewhere here. So this is 0.2, and this is here. So remember, this is a log scale, so this is non-linear. So like this is not like 1/4 of the distance to, like if this is 1/2 of the distance, that wouldn't be 1/4. That would be more like 1.6 or something. So I will just say this is like just like 1.6 maybe. Yeah. And what about this guy? So this guy here, this is 0.01, and this would be 0.02. So that would be like it's very close to here. So maybe that's 1.9 or something. So here that would be uh, that would be like sorry, that would be, let me think, it's a little bit confusing. I mean, looking at small screen here. Let me just try to do it again correctly. Let's start with the D60, yeah? Like D60 is equal to, and then D10, yeah? So the D60, like, see, this is the line, yeah? It is like, it's somewhere here, yeah? So D60 is somewhere here. And remember, it gets like, you see, as you see here, uh, so this is 1.2 here, okay? But like it get closer, like when you get near here, so that would be about maybe, so this is here 0.22, yeah, this is 0.2, so this would be 1 point, uh, here, you see, your, this is non-linear, so that would be maybe 1.6 maybe, yeah, maybe 0.16. How about this guy here? See here, you're very close to here, so that I will say this is maybe 1.0019, for example, yeah. So if you here, so that would be here, yeah. So if you divided like these two numbers, 60 by D10, so here that will give you like 8.4. So 8.4, this is larger than 6, so it is poorly sorted as we expected. How about this guy here? So this guy here, like you get like this value here, and you get this value here. So this value here would be maybe, it's not easy to get it. So like here, you get like, so this is 0.2, and this is, yeah, here. The 0.24, and like the 10 would be like here, uh, maybe 0.18, 0.18. So if you did this, then like CU is then 4, so it is well sorted. So as we expected, this is well sorted and this is poorly sorted. Again, it's difficult to read these numbers from this one, especially. I have a small screen in front of me. Maybe you watch it, you'll be bigger screen because I write on the screen. Okay. Anyway, so this is, I think in your homework you have to do one of these. Yeah. I mean, if you didn't get it very accurate, but at least you get that this is poorly sorted and this is like well sorted. But anyway, here we have the soil classification system. So this soil classification system is, as I mentioned, this is the ASTM, like whether you do like sieve analysis. So you have like 1, 2, 3, 4, 5, 6, 7. This is sieve number 7. This is 200. This is sieve 40, sieve 10, sieve 4, sieve 3. So you see, this is very different classification, for example, than the one by the sedimentologist. Here, this is a classification by the sedimentologist. This is a classification based on like civil engineers. Uh, and these are like the sieve number, sieve 200, that will be like the clay and silt. Sieve 6, that will be the fine sand. Sieve 5, medium sand, coarse sand, sand, fine gravel, and coarse gravel. So sieve and retained on, like, so basically here you will retain the coarse gravel, here you retain the fine gravel, sand, and here you will retain the clay and silt. Okay, in sieve 200. Okay. And then you calculate the percentage of the volume, yeah, like the ratios that you retained, okay, from the sieve analysis. Okay, so we looked at now like 3 factors so far. So we looked at the grain size, and I showed you the grain size at the packing, and I showed you like the packing is the determining factor, and we looked at sorting. So here like packing and like sorting, like you have, so we looked at grain size, packing, and sorting yeah, we look at the grain size, packing, and sorting. Okay, but another factor, it's like why clay has a like I mean, others than, like I will show you, like clay has small porosity, like high porosity. Reason, like, or one of the main reason why like clay has like a high porosity is because of the electromagnetic charge of the clay particle. So here, like this is a clay rich layer, and this clay rich layer, uh, clay and some clay rich soil, they have very high porosity, and this is because the dispersive effect of electromagnetic charge present on the surface of certain uh, like this book shape, like you see this book look like a book, yeah, See this book-shaped clay minerals. So you see this book-shaped clay minerals like sheets, one book on the top of one another, and this cause the clay particle like this sheets, they kind of create like electrostatic charges that make the clay particle repel each other, and this results in relatively large portion of void space like this sheets look here. And that's why like clay and silt porosity. So let's look here at let's just summarize. I think this is a good figure. Here you have crystalline igneous rock. It's a piece of rock, like a piece of marble, a piece of uh, gravel, a piece of marble, or a piece of granite. This has very low porosity and this has very low permeability. It does not conduct water. So it's very, like you see here, where would water flow here? Nowhere. Where is the porosity here? Nowhere. So this is like low, like the porosity is low and the permeability or effective porosity is also low. How about dispersive electromagnetic charge? This one has a very high porosity but very low permeability or effective porosity. It's not conductive. Low porosity, low permeability, or low effective porosity here. High porosity but low effective permeability. What about this quartz limestone? This will have like high porosity, very high porosity if it's like well sorted sand, like the porosity could be like up to 50%. So this has like high porosity and high effective porosity or like permeability. How about this guy? Glacial till. Glacier till, unlike clay, because this is something that is similar like to sand, but it is very poorly sorted, and you don't. So it's very poorly sorted. So because it's very poorly sorted, the porosity would be like low porosity, but and also the effective porosity would be also low effective porosity. So here you see the four cases like low porosity, low effective porosity or permeability, high porosity, low effective porosity or permeability, high porosity and high effective porosity, and here uh, uh, low porosity and low adds final. But okay, now if these guys like silt and clay, like why clay even has a higher porosity than silt if it's only the electromagnetic effect. Clay has this high porosity because also the grain shape. It's not only the grain size, but the grain shape. Because like you see here, if I have different grain shape, I can just fit them anywhere. Like I can fit something here, I could fit something here, I could fit something here, I could fit something here. So it is the grain shape with irregular shapes such as organic resulting in porosity higher than theoretically perfect sphere. So you can have like a porosity that's higher than the theoretically perfect sphere. Remember, which is 46 point like I don't know 55 or whatever. That is because of this irregular shape of organic material which does not pack closely, resulting in this high porosity. And that's why clay has the highest porosity. Again, this is just porosity, N, but the effective porosity of 5 to 5%. While the porosity for this one is from 33 to 60 like percent. Yeah. Okay. Uh, okay, so this is shape and packing of particle if not sphere can increase, like if not sphere can increase the porosity than the porosity of theoretically perfect sphere, which is this number. Okay. Now what we have been talking about now, this is called like primary porosity. So primary porosity, like here you have like the porous material, like the sand, for example, and yeah, and see this is where water can flow. So this is well sorted sand, and this is poorly sorted sand. But all this is called like primary porosity, like porous material, like well sorted sand, poorly sorted sand, sand, clay, till. All this is called primary porosity. There is something called secondary porosity. What is secondary porosity? So let's first read what is primary porosity. So I will read what is on the screen. So primary porosity developed as sediments or rocks was deposited or formed digenesis. So this basically like you have these sediments, how they were formed, and that will form like this primary porosity. Secondary porosity is not due to the sedimentation process, like how these because sediments could be deposited by water, they could be like deposited by air or whatever, and this what forms the primary porosity. Secondary porosity, this is formed subsequently to deposition. So like I have like sediments. So the sediments are depositing. This is secondary porosity after depositing. Like let's say you have like an igneous rock. What could happen is that this rock could break. Yeah, this rock could break, and when this rock breaks, this is called like a secondary porosity. We call this like fractured rock. Like you have a piece of granite that break or a piece of igneous rock basalt that break. This is called secondary porosity. Porosity develops subsequent to deposition. So you have like some igneous rock after they deposit it, when they break a rock, for example. Subsequent to deposit or formation of sediment or rock resulting in the dissolution of the original materials or fracking. This is a piece of granite. This is a piece of granite, and you see this is secondary porosity. We call this type of material, we call this like porous media aquifer. We call this porous media aquifer. This guy, we call it like fractured. We call this like fractured aquifer. So porous media aquifer, where does the water flow? The water flow between the sediment here. That's the porous media aquifer. Let me change the color. Or you can see it. I think you can see. The water flow between the sediment. In the fracture aquifer, where does the water flow? This is a piece of granite. Water cannot flow here. Water flow in the fracture. Yeah, that's where water flow. And for this, we don't use Darcy law. Like we will learn something like for this, we use like something called Darcy. Oops. For this, we call like Darcy law. For this, we don't use Darcy law. For this, we use something called cubic law. So this is Darcy law. This is cubic law. Are there other types of aquifer? Yes, there is a third type of aquifer, which is called like the karst aquifer. So this is called like karst aquifer. Karst aquifers that occur in limestone, and in karst aquifer, so that's a fractured rock. Like so, this guys like these two are fractured rocks. Yeah. This too is fractured rock. This is called like a karst aquifer. So the karst aquifer, this is in limestone, and when limestone dissolve, guess what will happen? Like karst aquifer, you could have fracture also, the rock can break, I will show you. But more importantly, the limestone, like the calcium carbonate, the limestone calcium carbonate will dissolve. And when it dissolves, what will happen? It will create like these fractures, and it will create conduits and even caves. Yeah, limestone. So that's called like a karst aquifer. In this course, we will mainly focus on the porous media aquifer. In an advanced groundwater hydrology course, you study like the cubic law, like the fractured rock, and the karst aquifer. But here, like in the karst aquifer, like here we use cubic law, here we use Darcy law, here what we can use. I mean, you can use anything or everything because, for example, like see this limestone, sometimes it could be porous, so it depends on basically the water will mainly flow in conduits and fractures. Mature karst or like other types of karst, the water could flow in the matrix, in the limestone itself, it could flow in the fractures, and it could flow in these conduits. So if you are modeling the flow in the matrix, you will use Darcy law. If you are modeling the flow in these conduits or the fractures, you will use cubic law. If you are modeling the flow in the conduits, you will use like an open channel flow, maybe like Darcy-Weisbach equation or something like that, or wave equation or something like that. Yeah, it's very challenging. Yeah. So let me show you like the karst aquifer. But the most important thing, the main thing I want you to learn here is what is the difference between like primary porosity and secondary porosity. Yeah. So primary porosity, that is like happened due to during the deposition, something will happen. The rock will break, the rock will dissolve. So when the rock breaks, that's usually in the fractured block, like in granite or the whatever basalt, and when the rock will dissolve, that would be in the uh, uh, limestone, yeah, the karst aquifer. So let me show you some karst aquifer. So let me walk you through like this, like in island doing some field work, and this is one of the wanted to go inside it and see what is inside there, and you see like so you see like see these things that I'm holding in my hand here. This is a light. See how this is a conduit. See how this conduit is. See how big this conduit where water can flow in it. So like if you just like water can flow in it, and so this is would be a cave. Like I'm just showing you part of it. And guess what are these dots? These are not bimos. Like you see these dots here. These are water. So basically, like water is flowing in the matrix, in the limestone itself, because it is old karst, so the water could flow. So here you can touch the water, you can drink this water, you can put your hand and like get some water and drink it. See this part here? As water flow over years, tens and thousands and millions of years, like see how here it is dissolving. This limestone will dissolve and this cave will open, and this is called secondary porosity. This is the same aquifer. You see here, this is a conduit, like he's how the rock is fractured. This is an outcrop of the same aquifer. So this is as a land surface, but you see here, you have a fracture here, you have a fracture here, you have a fracture here, uh, you have like a fracture here. To model like flow in this conduit, you'll use Darcy, Weisbach, or wave equation or whatever. If you want to model flow in this matrix, you'll use like Darcy's like Q big low. And that would be like I don't know, whatever. But here the most important thing, that would be like primary porosity. Primary porosity. And see this, and like this guy, this is the secondary porosity. Okay, let me show you. See, this is a close-up picture from inside. Like you see how the water drop. So over in this water, it will contain like calcium carbonate. So this thing will dissolve like here. That might be here. Yeah, and all this will be dissolved. Like will go down. Yeah, all this rock will dissolve, and this cave will picture here. You see, as the water is dropping, see the calcium. This water will be saturated with calcium. Yeah, and as the water, like you see these things and grow bigger and bigger and bigger. Yeah. Okay, so let's look here. Variation of porosity of unconsolidated material, rocks and plume. So here, uh, this is would be like a volcanic rock, like basalt, like in Hawaii, for example. So Hawaii, this is like a volcano. So Hawaii, this island, it's an island in the middle of the ocean. How did it happen? It's just a volcano happened, yeah. So that's all this black rock. It's black rock, like big island in Hawaii. You will find the landscape is black. It's still black because it's still geologically active. Like the big island in Hawaii is still geologically active, and you will see the landscape would be this black rock, like this black. So if it's unfractured, it will have very, very, very almost zero porosity. If it's fractured, it could have like very high porosity. Fractures, again, like fracture would be things like that, like you see these fractures. If it's intrusive igneous and metamorphic rock, again, fractured and unfractured. So this would be like a granite, for example, or marble. So it will have, that would be the porosity. Limestone without solution, limestone with solution and opening. So this without solutional openings. So this is just the limestone, the primary porosity of the limestone. And this is would be like if you added the secondary porosity of the limestone, it could be where you have fractures, and it be goes up till here. Mudstone, sandstone, collago, it's difficult for me to pronounce this word, collagomerate. Yeah. And then here, gravel, sand, silt, and clay. So silt and clay could be up to 70%. And now we know why these could have high porosity. Sand and gravel, we know that this is a theoretical limit, yeah, for them. But here, that would be, we know why. So here, this is because like charges. Here, that would be because of like not particle size, but because of sorting and packing. Yeah, and the clay is very high. That could be also because of the shape. Okay. Anyway, how could we measure or estimate porosity? One way is we can do like geophysical measurements, so borehole geophysics like gamma ray, nutrient log, density logs. That's one way of doing it. And each different material will show like different values for this one. Again, I'm not going to go through this detail, but I just want you to be familiar with it. If you need to use like any of these methods, gamma ray log, nutrient log, and density log, you can just learn them. Yeah. But the other way is that like we do it in the lab, like in a lab experiment. So basically, this is like an oven. Like you get the material, so here, that's the procedure would be simple. Like objective is like water displacement method, like estimate the volume of water needed to saturate the sample, volume of voids for the for for two types of sand. Like here, this is sorry for two types for here this should be two for two types of sand. So procedure, you will be giving glass beakers containing two types of sand. So like you have this sand and this sand. For each measure the volume of sand, like you measure this volume, you measure this volume. Take an empty cylinder and fill it with water and record the water. Pour the water into each beaker containing the sand until water just reaches the surface of the sand. Record the volume of water left in the cylinder. So you see like you know how much water you started with, and then you see how much water is left, and then you will know how much water is here, and then you do it for both of them. So the result, so here if you did like and then uh, and then for the initial water volume in the cylinder was 100. For sand 2, initial water volume of the cylinder was 100. For sand 1, water left in the cylinder was this. For sand 2, water left in the cylinder was this. This is the sand volume 1, sand volume 2. So basically, like if you did this, like you can find like uh, so like try to do this, yeah, like pause the video, yeah, and try to do this calculation, like volume of the void space, which would be like the volume of the water and the volume of the sample, yeah. So try to do this and calculate the volume, the sand one, like the porosity of sand one, and then the porosity of sand two, yeah. The volume of the void space would be that in that case like the volume of the water, yeah. Okay, so try to do this and pause the video, try to do it, and I will give you the answer. Okay. Okay, so welcome back. So the answers that you should get if you did it correctly. So porosity of sample one should be like this is what I got, and porosity of sample two, this is what I got. Okay, so that is this exercise. Okay, again, let's just review what we did in this lesson. So effective porosity, that's porosity available for water flow. Effective porosity is also referred to as porosity of mobile water, percentage of pore space filled with mobile water. And again, silt will have high porosity. We know now why, but low effective porosity. Fine sand, coarse sand, and sand gravel, they will have lower porosity, yeah, but higher effective porosity. And now we know why, because you can have this passes where water can pass. Okay, so now let's go to a related term that is related to effective porosity, which is like specific yield. Yeah, so we will do next something called like specific yield. And specific yield, this is the ratio of the volume of water that drain from a saturated rock owing to the attraction of gravity to the total volume of the rock. So for example, if that was like here, like for example, let's say this is uh, my sample, yeah, and then I put it like in a beaker or whatever, yeah, and then I put a screen here so that the sand will 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 not fall down. So I put like this is the screen here so that the sand will not fall down, and then I opened like there is a cover here. I open the cover so that only the water will pass. So what will happen? So you see like this water here, it can flow down. It will drain. This water here 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 will drain. This water will not 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 drain by gravity. See, this is called like specific yield. So specific yield basically it is the ratio of the volume of water that drain from the saturated rock, not the total volume of water, because some water will not drain. Why? Some water, you see, is stuck here. It will not drain. See, the water that's stuck here will not drain. Some water will be stuck like due to surface tension on the clay mineral. So you will see some water stuck here due to surface tension. It will not drain by gravity. Yeah? So this is called like a specific yield. Yeah, and obviously this one, fine sand, coarse sand, and gravel will have specific yield would be very high. Silt, the specific yield of silt will be very low because they have low effective porosity, while this guy, they have high. So let's look here. So specific yield, yeah, let me read it again, is the ratio of volume of water that drains from a saturated rock owing to attraction of gravity to the total volume of the rock. Yeah, so here that is the total volume of the rock, which has like pore space filled with water, and that would be the ratio of the volume that drain from the saturated owing to attraction by gravity. Yeah, so here, so for example, see this is like, let's say like you have a screen here and you open, see that much water will drain. For example, if that was clay, only like little amount of water will drain, like not much water will drain. Yeah, much smaller amount of water will drain. And like, so, or alternatively, like like you have a sample, like have two samples. Yeah, let me show you. I have two samples. This is like sand and this is clay. If I open like the screen here and like let this water drain, let's say like in 10 minutes, yeah, I will have maybe that much amount of water. If that is will drain because the flow is very slow and not much, yeah. So that is called like a specific yield. So the volume of water drained by gravity over the total volume of rock. And see, that's what exactly what I was telling you. So it cannot release water when gravity force equal to surface tension, called pendular water. Yeah, so even if in the sand, like as I showed you before, like so this is sand, yeah. So when you open this, water will drain, but not here due to surface tension, yeah. Some water will be coated here due to surface tension. So even though it is sand, not all the water will drain due to, or gravel, not all the water will drain due to surface tension. So porosity can be the same as porosity force equal to surface tension. Porosity can be the same as surface here is a smaller, finer material, larger surface area. So like porosity, like if you have the same porosity, the specific yield is smaller for finer material because you have larger surface area. Like so gravel, yeah, like you can have something here, so that's like a gravel. But sand, like you see here, if this is sand, for example, like you have something here, you have something here, you have something here, you have something here, because you have larger surface area, so the specific yield could be smaller. Like you see here, the specific yield of of sand is smaller than that of a coarse like gravel. The specific yield of clay is very small. Yeah, very small. So porosity, so this is another definition that I would like to give you for porosity. Porosity could be equal to specific yield plus a specific retention. Yeah, because remember, like the pore space here, specific yield, like the water that will be retained here, that will be your void space, because specific yield and the specific retention, that will be the volume of void. Yeah, uh, that will like be surrogate, like to calculate like the volume of void. Yeah, like because that's over the total volume of rock. Yeah, so that's so specific yield here, the volume of the volume of we call this like, what name did we give it here? I have a name for it. That's just to be consistent here. V, no, yeah, VE. So here, this would be like the specific yield, that is the volume of E, like let's call it E, and mobile water over the volume of immobile water. Sorry, this is the volume of mobile water divided by the total volume, and specific retention, that would be the volume of immobile water over the total volume, and then that's why you get like the porosity could be, yeah. So porosity could be like volume of immobile water over the total volume, and that this is a specific yield and this is a specific retention. Yeah, so water is retained. Okay, so here this is the final slide that I have in this lesson. Uh, so you see here like the silt size, yeah, in percentage, sand size in percentage, and the clay size in percent. Like if you are looking at the clay, the clay size in percentage uh, with so this is like you see here, this is the clay. The sand is very like small amount, and like most of it would be like silt and clay. You see like silt and clay sand would be very small, and sand, clay, silt, silty clay, and basically like what you see here, that would be the percentage in the sample, and that would be the specific yield. Yeah, so here like the specific yield is very small, versus if you have like very small like silt and the clay size and very large and very large portion of sand, like it's almost sand, then you have very high like specific yield. So here this is sand and this is clay, and you can see here like the clay, the specific yield could be 0, like to 5, the average is 2. Where so if you have a coarse gravel uh, or like coarse sand, for example, yeah, you could have like a very high like specific yield. So basically this figure, specific yield, N is gravel and sand, small specific retention, specific yield is much like, so specific yield is close to like porosity, if gravel and sand, because it has small specific retention. Just remember, like n is equal to specific yield plus a specific retention. So for sand, like this is very small, and this is very big. So specific yield is almost equal to porosity. Versus like in silt, uh, in like silt and clay, like the in silt and clay, the n would be equal to specific retention. That's for clay. Specific retention, that is for clay and silt. Approximately equal to specific retention. And we will look at these things in more details later, yeah? But just know this, that clay will have a very high specific retention, and sand and gravel will have very high specific yield. Okay. So that's all for this video, and I kept my promise by keeping like the videos for this week, both of them less than 150 minutes. Okay.